Okay, now I want to walk you through an example of how this will work. When you get to the lab on Tuesday, you're going to have 2 glass vials in your hood. They're going to be stoppered with corks. And one of them will have a liquid in it and one of them will have a solid in it. And your goal at the end of the 3-week period will be to have identified both of these compounds. So for this example, we're just going to do one compound, a liquid. It is a clear, colorless liquid and it smells sweet. The student is going to go through and you do your solubility tests, and you note that the liquid is insoluble in water. When you add a few drops of this to the test tube, it floats on the water. It does the same in 5% hydrochloric acid and 5% sodium hydroxide. It is, however, soluble in concentrated sulfuric acid. You're then going to go through and take a boiling point, and that's described in your procedure. You see a steady rise in temperature until about 210 degrees Celsius, and the temperature stays steady between 210 and 212 Celsius for about a minute. You went ahead and stopped the heating before the test tube boiled dry. So, what can we conclude about our unknown? What could it be? What is it likely not? Let's take a quick run back to our solubility data and interpret what we've seen based on our liquid. Remember, what we saw is that our compound was insoluble in water. So that means that it doesn't necessarily mean that it's not an alcohol, but it means that it's not an alcohol 1 to 5 carbons. So I think we can safely conclude that our compound is larger than 5 carbons. It was also insoluble in hydrochloric acid, so we can safely conclude that our unknown is not an amine. Our compound was insoluble in 5% sodium hydroxide. Since it was insoluble in sodium hydroxide, we didn't even need to do this bicarb test. We know that our compound is not a strong acid or a weak acid, so we don't have a carboxylic acid. And we don't have a phenol. And a phenol, remember, is just an alcohol attached to an aromatic ring. So, what we know at this point is that we probably have an alcohol, aldehyde, ketone, ester, amide, ether, halide, or hydrocarbon. We then did the concentrated sulfuric acid test, and we saw that was soluble. So this means that it is a compound containing oxygen or nitrogen, or it is an unsaturated hydrocarbon, or it could be some of the aromatics. So we look back at our neutral molecules. The compounds containing oxygen and nitrogen include the alcohols, the aldehydes and ketones, the esters, amides, and the ethers. Or we could have a hydrocarbon. So we don't have a lot that we can conclude in the positive, but we have a lot of things that we know in the negative. We know we're bigger than 5 degrees, we know we're not an amine, and we know we're not a carboxylic acid. So that is actually fairly useful. So we're coming back over here. We know that we don't have a carboxylic acid, an amine, or a phenol. But we know that this is likely some oxygen or nitrogen containing functional group, or unsaturated. So, if we were doing a strict qual scheme, now we would get out a whole bunch of test tubes and we would begin testing for an alcohol, for a ketone, for an ester, for an aldehyde. That does not sound very fun. So, but fortunately, I'm not letting you do that. What you're going to do instead is you're going to go and take your IR, and we're going to need to interpret it. So let's do some of the tricks that we learned back in the IR chapter. So there's a dividing line at about 3,000, where the things that are immediately below 3,000 tend to be your sp3 hybridized carbon to hydrogen, and pretty much everything has sp3 hybridized carbon to hydrogen, so that's not super useful. But what is really useful here is this sp2 hybridized C to H that is probably here. And that's interesting because we did think that we might have some unsaturation. I've got a very strong peak right here, and fortunately your IRs, you will be able to do peak picking here. This peak is at about, I don't know, 1680, 1700. Peaks at about 1700 indicate carbon-oxygen double bonds, which is cool because we had a good idea we had a carbon-oxygen double bond based on the solubility test. Now, because we've got sp3 hybridized C to H, we want to think some about whether or not we think we have an aromatic or an alkene. And if we look really hard, we actually see some peaks here that are indicative of aromatic, including the CH stretch. We've got some faint overtones, and we've got some out-of-plane bending. And this may not be something that you can see right away, okay? I only was looking for it because I was keeping in mind that idea of the unsaturation. But that may not be something that you pick up on right away. What you probably should have picked up on is your carbon-oxygen double bond stretch and the idea that you've got some unsaturation. Now, if you picked up on the fact that you have this carbon-oxygen double bond and the idea here that we don't have a CO single bond stretch here and we don't have anything that's really indicative of an aldehyde, you could probably go ahead and go to the functional group tables. If you weren't doing the IR in this level of detail, and a lot of you don't yet, and that's good because I don't want you to, what you might have to do is go to your NMR, and you'll get this NMR from me. There are 2 videos on Canvas that are show me videos that show you how to interpret these NMRs in detail. This is your C13, this is your proton NMR. Okay? Now, what we need to use this NMR for right now is we need to try to get some ideas about some things. We need to decide what's going on with this unsaturation. Do I have an alkene or an aromatic? Also, since I have a carbonyl, do I have any indication of whether I have an aldehyde, a ketone, or an ester? And that's all I'm going to use this NMR for right now. Now, if you go to your tables that go with your NMR correlation tables, one of the things that you'll realize is that if you have an aromatic ring, you're going to have peaks from 6.5 to 8. And there's probably going to be a lot of hydrogens in that region, considering aromatic compounds are going to have anywhere from 1 to 5 hydrogens. And lo and behold, I do see some protons from 7 to 8. So these are probably my aromatic ring to hydrogen. Now, your peaks for alkenes tend to be from 5 to 6.5. I don't see any peaks in this region, so I probably have no alkenes. Aldehyde protons tend to be from 9 to 10. I don't have any of those, so I know I don't have an aldehyde. Figuring out whether or not you have a ketone or an ester actually is something that you do within the C13. So when you look at your tables for C13, what you're going to see is that there's a peak right here at just above 200. Ketones tend to have chemical shifts from 190 to 220. Esters tend to have chemical shifts from 160 to 180-ish. So since this little peak, and it's very short, is just above 200, that gives me a really good clue that I have a ketone. So I'm going to take that piece of information and I'm going to go to my unknown tables. Your unknown tables are posted on Canvas. They are an Excel spreadsheet and they are a tabbed spreadsheet. So when you open it up, it usually opens up to the phenols. For each functional group, you're going to start with the liquids, and there's no solid phenols used in this experiment. All of the molecules are then listed in order of increasing boiling point, and there are going to be 1 or 2 derivatives listed for most of the functional groups and their corresponding melting points. And actually for these phenols, there's 3. What we're going to do is we're going to click on the tab for the ketones so that we can see our our possible candidates for ketone. And in order to get the screenshot to show us what we needed, I did some clipping here, but you can get the gist of it. Now, The melting point, or the boiling point that we observed with our unknown was 210 to 212, I believe, 213 degrees Celsius. What you're going to do for this table is you are going to go plus minus 25 degrees Celsius, and you're going to write out the names and the structures of all of those possible molecules. So what that means is that you're going to be considering as possible candidates for your unknown all of the molecules between 185 and 238 degrees Celsius. So that would be all of these. And you're going to need to go ahead and write out in your notebook all of these names and all of these structures. This is the step that nobody wants to do, which is writing out the structures. If you do not write out your structures, you can't compare them easily to the NMR, and I will not be able to answer any questions or help you out. So why don't you go ahead and go to Canvas, open up the spreadsheet, and get to the place where we just were, and go ahead and practice drawing out all your structures. Pause the video right here and go do that.
Carbon in its ordinary form is coal. Crush it together and diamonds are born. Come on and meet the elements. May I?
Okay, so we've used our knowledge of IUPAC nomenclature and gone online for a couple structures that we needed, some of the common names. But what we've assembled here is drawings of all the structures that were plus or minus 25 degrees from our boiling point. Now we can look at our NMR, and I encourage you to look on Canvas at the Show Me videos that'll show you how to interpret these particular Aldrich NMRs, the carbon and the C13. When we looked at this NMR earlier, we determined that this region of the NMR is for protons that are bonded to aromatic rings, and we can see that we have several signals in here. If we go through and we figure out our integration ratios, and we do that by measuring the heights of each step and then looking at the ratios of the heights, and again that's brought out in the Show Me videos. When we do that, we will find that the ratios of these height are in a pattern of 2 to 3 to 2 to 3. We're saying that this signal has 2 hydrogens, this signal is describing 3. Actually, there's 2 signals here that are very close together, but they're integrated together. We've got this 2 hydrogen quartet right there and this 3 hydrogen triplet. Now what I'm going to do is I'm just going to take and think about these protons for a minute, and I'm going to head back to my structures. And since I know that I have 5 protons that are attached to aromatic rings in my structure, so there's something else there. I know that my unknown has this structural feature somewhere, so I can start crossing out any molecule that doesn't have an aromatic ring. And more to the point, I can cross out any molecule that has an aromatic ring, but that aromatic ring doesn't have 5 protons on it. So once I've done that, I can actually see that I've eliminated quite a few molecules, and now I only need to think about which one of these 7 molecules matches my NMR really well. So now I want to think about this. I've got this 2 hydrogen peak that indicates a CH2. I've got a 3 hydrogen peak, so that indicates a CH3. I'm not even going to worry about the splitting. I just want to think about the fact that I know my molecule, in addition to the aromatic ring, has 1 CH2 group and 1 CH3 group, and that's it. So now I can go back to my drawings, and I can start eliminating in some things. So for example, this molecule only has a CH3, no CH2. So I can get rid of that. This molecule has a CH2 and a CH3, so it can stay. This molecule has a CH2 and a CH3, so it can stay. This molecule has a CH group, a methine, and 2 CH3s. Well, this would give us a 1 hydrogen peak and a 6 hydrogen peak. That doesn't match our NMR, so out it goes. This one has a CH2, a CH2, a CH3. It doesn't match. CH2, 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 CH3. This has 3 CH2s. It's gone. And last but not least, this one has 2 CH3 groups and a CH, so it's gone. So now we're down to just 2 possibilities, molecule 2 and molecule 3. Now we'll go back to our NMR again, and I'm going to go ahead and draw both of these molecules out so we can look at them and see what we think we're looking at here. And we can look at this 2 ways. We can either say, okay, I'm going to look at this structure first, and I'm going to say this CH2 group I know is next to a CH3. So I would expect this CH2 group to be a quartet because it is next to a CH3. If I look at this molecule, this CH2 group is next to 2 quaternary carbons. Neither of these carbons has any hydrogens on it, so I would accept this to be a singlet. My 2 hydrogen peak would be a singlet if it was this molecule. If we apply the same logic to our CH3, I expect this CH3 group to be a triplet. N equals 2, N plus 1 equals 3. This would be a triplet. If it's this molecule, though, I expect this CH3 to be a singlet. And if I compare to my NMR, it's a little hard to see, but what we can see here is what I have here is a quartet, and what I have here is a triplet. So this NMR better matches this molecule. So my working conclusion is that this molecule right here, turns out this was named propiophenone, is my hypothesis of what my unknown is. Now we're going to go back to our unknown table one more time, and we're going to look at making our derivative. So I'm going to go to this line for propiophenone. Oops, I was hoping that was a little more opaque. Sorry about that. And what I see for propiophenone is that there are 2 unknowns that I could make for it. One would be the semicarbazone, which has a melting point of 173, or I could make the 2,4-DNP derivative, which has a melting point of 193. So in the case of propiophenone, I could make either one. Now let's talk about what these derivatives really help you do. If you look right here, propiophenone and phenylacetone and isobutyrophenone all have very similar melting points, or boiling points. They're all very close together. But look how different their derivative melting points are. So if you had a solid and you didn't have an NMR and you were trying to tell the difference between phenylacetone and propiophenone, what you would do is you would take whatever your solid is and you would make this semicarbazone derivative and you would check its melting point. If its melting point were closer to 173, you'd know you had propiophenone. If it was closer to 198, you'd know you'd have phenylacetone. Or you could make the 2,4-DNP derivative. This might even be a better one to make because look at the big difference in the melting point. The propiophenone derivative has a melting point of 190. The phenylacetone derivative has a melting point of 155. Now, what are these derivatives? Well, what these derivatives are is their reactions. So you could imagine if I took propiophenone and the derivative reaction would be to make what one of the possibilities, the 2,4-dinitrophenylhydrazone derivative. And it actually looks like this. So that would be the 2,4-dinitrophenylhydrazone you would make from propiophenone. But if you made that same derivative From the isobutyrophenone, that molecule would be this. And these two molecules are going to be very, very different in their melting point. This one has a melting point, like I just said, of 190. This one has a melting point of 155. And why we use these dinitrophenylhydrozones is the fact that this group on it, this is the dinitrophenylhydrazone, this is what's actually going to help make sure that one of the properties of this group on a molecule is that the molecule winds up being a solid. So what you're going to do is you are going to make one derivative for your solid unknown and one for your liquid, assuming that it works. What do I mean by it works? Well, if you look right here, you're going to see some dashes. And what these are is these are examples of molecules that if you try to make a 2,4-DNP derivative of it, it won't work. Either the reaction will fail or the product of that reaction isn't a solid. And since our whole point of making a derivative is to take a melting point, if something doesn't make a solid, that's not going to accomplish what we need. So when you're ready to make your derivative, you're going to want to pick a derivative that is easy to make for the molecules that you think your unknown might be. Okay, so what's our conclusion and does it fit the data? Well, our conclusion is that that our unknown is propiophenone, does it fit the data? Well, we had a melting point of, I believe, around 212 degrees. The literature value of the melting point of propiophenone is 218. Excuse me, that was a boiling point. It's 218. So it's reasonably good agreement. Why is ours a little lower? Hard to tell. Maybe some purity issues. Maybe our thermometer wasn't calibrated. It's hard to say. Does that match our solubility? Well, if we look at our molecule, it's a ketone and an aromatic, and it's larger than 5 carbons. It isn't an acid, it isn't a base, so I wouldn't expect it to be soluble in anything but H2SO4. So that matches. What about our IR? Let's take a scroll back and take a look at our IR again. If we take a look at our IR, what do we see? We see sp2 and sp3 hybridized carbon to hydrogen, and that makes sense because we have our aromatic ring hydrogens that are giving us our sp2, but we also have this alkyl chain right here which has sp3 hybridized carbon to hydrogen, so that all makes sense. We have our ketone, our carbon-oxygen double bond, and on yours, because RIRs do a much better job of peak picking, you can correlate your wave numbers much better. We can then compare our overtones and our out-of-plane bends to the table in Klein and verify that these are the monosubstituted aromatic patterns, the peaks that we expect to see for the out-of-plane bend and the overtones, and this is also a peak that's common in your sp3 carbons. So it matches the IR really nicely. So as we just saw, our IR matches. We actually used our NMR to build our structure, so our NMR matches, and we'll take a look at our derivative data and see if that matches. And assuming all of these match, then we can conclude that our unknown was in fact propiophenone, and we can then fill out the report form and turn it in and earn our points. So hopefully this helped you see kind of how all the pieces are going to come together. Please come and see me for help. You want to make sure that you're not wasting a lot of time getting really confused and getting frustrated when one of the big goals of this exercise is for you to come and actually talk about experimental data with me. Thanks for watching, and I'll see you in the lab.